Good morning, good afternoon, good evening, depending on wherever you are watching this or listening to this weekly science review. Weekly Science Review is a weekly event organized by Vetri Labs, where we look at published electrochemical literature that's in open access mode. We here at Vetri Labs focus on enabling electrochemical technologies and implementation of those technologies at scale. Today's discussion is going to be led by Dr. Ayyappan, who is a research scientist at Vetri Labs. Over to you, Ayyappan.
Okay, everyone can see my screen.
Yes.
Okay, so yeah, today we'll be discussing about this paper, copper-doped zeolitic imidazole frameworks, which is short form Zif-8, a new generation of single-atom catalyst for oxygen reduction reaction in alkaline media. So before going into the paper, just giving an overview of oxygen reduction reaction. So oxygen reduction reaction is a part of a polymer exchange membrane fuel cell on the cathode side, and it is a kinetically sluggish, and it's one of the main limiting factor in the performance of your PEM fuel cells. On that, to have the oxygen reduction reaction, platinum support on the Vulcan carbon is the state-of-art ORR catalyst. So ORR can actually happen through different pathways. So you ideally want it to be more efficient. You want them to be a 4-electron reduction. So where the oxygen gets converted into water in terms of acidic, or hydroxide ion in terms of alkaline solutions. Or there could also be a possibility where it is an indirect 2-electron process that is in acidic medium. It has a peroxide ion formation. I actually missed this. So this should be alkaline and this should be acidic. So it has peroxide, and that peroxide, before diffusing into the electrolyte, it gets converted back into water. So it's an indirect 2-electron process. And there are some catalysts that cannot go past this peroxide state, and they basically do a 2-electron oxygen reduction reaction. And so what is the need? So what is the problem with the state-of-art catalyst, and why people are working on the alternative catalyst, right? So we all know platinum is an expensive material. So, and also the availability is very limited. And in terms of the catalytic activity, they have a very good catalytic activity, but they suffer from a poor stability when they're operated at like for a longer cycles. And also, depending upon the ORR reaction in which fuel cell it is employed, in terms of direct methanol fuel cell, they suffer from methanol crossover. When methanol crossovers from the anode side, that could get reacted on the cathode side and decrease your activity of your cathode catalyst. And also, they're susceptible to this carbon monoxide poisoning. And so one of the main alternative catalysts that people have looked at is going noble metal free catalyst. So it's basically MNC, which is a transition metal nitrogen carbon combination catalyst. The advantage of that is it's very low cost, and then also it has a good catalytic activity in alkaline medium, and also there is improvement in the acidic medium also. And they have an extremely good stability, and also they're resistant to this methanol crossover and carbon monoxide poisoning, which is a problem with the platinum-based catalyst. So, and using metal organic frameworks, people have started to create this MNC catalyst. So before going into that, let's just give an overview of what is metal organic frameworks. So metal organic frameworks, or can also be called as a porous coordination polymers, they have become they're a self-templated precursors for this preparation of this carbon material, as I mentioned earlier. And they can be considered as low-cost materials depending upon the metal source we employ for the preparation. And they are crystalline porous materials that is composed of both organic and inorganic components in a rigid periodic network structure. So you can modify metal organic frameworks with binding sites that can have like reactive nitrogen that can bind to this organic iodides, right? So you basically have this metal ions, and then organic linkers undergo a reaction. So the common methods of preparation could be, you can have a solvothermal to get a nanoscale morphologist, or a short synthesis system, go for a microwave, or multiple different methods you can do to produce these MOFs. And they have very high, they have different attractive characteristics, such as they have a atomic level structural uniformity, and they also have an excellent chemical compatibility in both organic and aqueous media, and they have a uniform pore structures, and their topography is tunable depending upon your application, and they can also have a very wide chemical functionality. So this MOF, metal organic MOFs, finds its application in multiple region. So one is with the gas storage and separation. So because MOFs advantageously can serve as a good absorbance at a very low temperature. And also the MOF absorbent can be recycled multiple times without the loss of capacity. And they can also be used in drug delivery or also in chemical sensors or also on heterogeneous catalysis. So, and in this paper, they are focused on the zeolitic imidazole framework, which is ZIF-8. So basically, ZIF-8 is a representative MOF and a mixture of zeolite containing a cubic sodalite framework, which is prepared by zinc, linking zinc ions with this 2-methyl imidazole. This is the organic linker. They basically have the zinc 2 plus and then the organic linker coupled together to form this ZIF-8 MOF. So, and the advantage of using ZIF-8 is it is favorable for this generation of this 3D highly porous carbon framework with this formation of this MNC structure, which is important for getting this good catalytic activity. And it also has many advantages, like it's easy to synthesize, and they have an adjustable particle size, and they have a excellent thermal and chemical stability, and they also have a good commercial availability. And of course, they have a high nitrogen content, so you can easily form this MNC structure. And they're also very highly porous with the average of 1800 meters square per gram surface area. So in this paper, this is to give an overview of the schematic illustration of their synthesis. So they mix copper nanoparticles and the ZIF-8 formed from the zinc 2 plus and the linker, and they sonicate it, and then they stir it for about 1 hour in a methanol mixture at a room temperature, and they form this copper ZIF-8. And then to form this MNC, the copper ZIF-8 needs to be pyrolyzed, and they do this in nitrogen atmosphere to form this copper doped nitrogen doped carbon. And in this slide, we can go over how each of this material is synthesized. So first they synthesize this CTAP capped copper nanoparticles by having 1.5 gram of copper nitrate trihydrate mixed with 106 milligram of CTAP in methanol as solvent, stirred for 3 hours. And then they finally used the centrifuged, and the precipitate was washed with methanol and vacuum dried for about 6 hours at 80 degrees Celsius. And then ZIF-8 synthesis is using 0.9 gram zinc hexahydrate nitrate and 11 gram of 2-methyl imidazole, which is MIM in short form, both dissolved in 50 ml of methanol and stirred for about 30 minutes. And then the resultant mixture was sterilized over 2 hours. Then centrifuged, the precipitate was washed with methanol and vacuum dried for about 24 hours at 80 degrees Celsius. Then the final would be the synthesis of copper ZIF-8, and then finally converting that to copper nitrogen doped carbon, which is an X is the temperature that they do the pyrolysis. So we're ranging from 500 to 900 degrees Celsius. So here they used ethanol as a solvent, 40 ml ethanol with 0.21 gram ZIF-8, sonication for 3 minutes, and then mixed with 0.21 grams of copper nanoparticles mixed in 10 ml ethanol, stirred these two mixtures for about 1 hour at 80 degrees Celsius, and then centrifuged the precipitate, centrifuged it, washed the precipitate with methanol, vacuum dried it for about 80 degrees Celsius for overnight. And then finally, the product is your copper ZIF-8. So they took 250 milligram of the copper ZIF-8 and annealed it in like about 20 ml per minute of nitrogen for a total time of 2 hours and between different temperatures, and they named it with X, which we'll see and what is their activity in the later slides. So to confirm the presence of copper doping in the ZIF-8, they did this XRD characterizations. And as you can see, the synthesized copper doped ZIF-8 as a BCC crystal lattice symmetry. And then we can see that the structural integrity between the ZIF-8 and the copper ZIF-8 is maintained. It's not changed much because the copper ionic size and the zinc ionic size are almost the same. And then with this calcine ZIFs, you can see this high absorption peak at 23.4 degree and 43.5 degree, corresponding to the amorphous and the graphitic carbon. And also for the copper with nitrogen doped carbon, they have other two peaks with that about 43.2 degree and 50.4 degree, corresponding to this metallic copper of Cu111 and Cu200. So they have, which suggests that the presence of zero valent copper. And then apart from the formation of this graphitic structure and amorphous carbon pyrolysis, they also have two large peaks about showing the diffraction of 002 and 101. And one thing maybe they kind of missed is maybe the XRD analysis. They said the copper addition has no apparent effect on the ZIF-8 structure. And then, so then they did the specific surface area characterization. So this is very critical because I mentioned earlier that ZIF-8 has a very high porosity, and majority of those porosities are basically about it has about like micropores. So the micropores, it's very it's about 2 nanometers, right? And then it's mesopores. So you also want micropores and you also want mesopores. So in your catalyst, so the micropores can assist in your catalytic active sites, and mesopores can help with this mass transport. But ZIF-8 is mostly with micropores, so it could limit the mass transfer, and that's basically the reason they also try to convert it, like to undergo carbonization and convert it into carbon. So you have a mixture of both micropores and mesopores. So you have both high active sites, and also you have a good mass transport. So to confirm that, they need the specific surface area characterization. So as we can see, the ZIF-8 they synthesized has about 1437 meters square per gram surface area, with a pore volume of about 0.65 centimeter cube per gram. And the average pore size is about 6 nanometers. I think the average pore size is kind of on a larger number because they have a couple of macro pores that just makes this number larger. And they're representative. And then when they do this copper ZIF-8, right? So it's then the porosity, also the pore volume decreases, surface area decreases, and the nitrogen doped carbon has a higher porosity when you compare to the copper doped nitrogen doped carbon. So these kinds of tells us the copper NC and the nitrogen doped carbon has a micropores less than the copper with ZIF-8 and ZIF-8. So this could be because of the collapse of the certain structures inside the MOF. So that's why there is a decrease in their micropores. And also the heavy metal zinc undergoes gets volatilized, and then it gets evaporated, and then the carbon gasification can also be attributed to this development of this mesopores in the nitrogen doped carbon and copper nitrogen doped carbon. And also you destroy this cubic structure at a very high temperature, right? So that is the one that is attributing to this presence of more macropores. So as a result, we could see on this inset here, you can see that comparing to the ZIF-8 and then the copper with nitrogen of carbon 900 degrees Celsius, you can see that there is a decrease in the micropores, and it's mostly mesopores and macropores. So for an ideal 3-dimensional porous structure as a good catalyst, so you need to have a synergistic effect from all the different pore sizes. And so this could reduce the resistance to mass transfer, and also it can expose more ORR active sites on your catalyst surface. Then did some SEM-TEM analysis to confirm the structure of the obtained ZIF-8. So as you can see from the SEM images, it's seen that it has a well-defined dodecahedral structure with a truncated rhomboid, which is a typical ZIF-8 morphology. And also these findings suggest that the ZIF-8 surface morphology and the skeleton structure did not change when they are trying to dope with copper nanoparticles. And you can see that it has about, when the high resolution TEM, you can see this lattice fringes about 0.285 nanometer despacing, which belongs to this 111 crystal surface of CuN3. And also they did this EDX analysis to confirm the mass, weight percent and atomic percent of each element. And you can see the atomic percent of copper is about 0.46. And you can see zinc is almost kind of reduced because zinc gets evaporated at that high temperature, and which gets, so it makes the availability of nitrogen there, and then the copper gets doped, and then it gets linked with the nitrogen present in the MOF. And also with this elemental mapping, they can see that is a uniform dispersion of different elements, confirming the presence of copper in their finally obtained structure. And also in the TEM, you can further see that the composite metal nanoparticles are coated in the carbon layer or at the top of the carbon. So this kind of makes the structure is conductive, right, with the copper, and also it could improve the stability of the catalyst, at the same time avoiding the active sites getting directly exposed in the electrolyte. So in terms, you have a good stability. Next, they did the FTIR and the TGA. So with the FTIR, you can see a sharp peak at 423 wave number, which is caused by this zinc nitrogen stretching mode, suggesting that the linker zinc and the nitrogen atom are bound to this, bound to form this porous ZIF coordination structure. And you can eventually see this peak is getting is not present in this pyrolyzed nitrogen, pyrolyzed copper doped nitrogen doped carbon at 800, confirming that zinc is completely removed and there is no zinc nitrogen bond. Also, a couple of other CH vibration was assigned, was from the peak at 1100 to 1300, and the stretching vibration is put for the peak at 1466 and 1470. And additionally, there was two other peaks at 1229 and 1231, confirming this C bond N in this imidazole ring. And also the copper nitrogen bonding was confirmed within this range of about 550 to 620 centimeter inverse. Also to confirm the TGA, so the TGA curve, as you can see, it indicated a very low loss of about less than 0.5 from 20 to 200 degrees Celsius. So this corresponds to this removal of the guest molecules from these cavities present in the MOFs. And we can start this methyl imidazole linker decompose above 350 degrees Celsius, causing this weight loss. And you can see a sharp weight loss about 63 to 64% is for like temperatures between 400 to 500 degrees Celsius on ZIF-8. And the final product would be basically zinc oxide on ZIF-8, and also on copper ZIF-8 also it will be zinc oxide. Then to further characterize this, what is the presence of copper? What is this? What is the chemical composition? What is the elemental state? So they did this XPS analysis. And before going to copper, let's see on the nitrogen. So basically, nitrogen can actually have four atomic configurations with the pyridinic nitrogen, pyrrolic nitrogen, and graphitic nitrogen, with an oxidation nitrogen, which is basically the pyridinic nitrogen at the edge getting oxidized to form pyridonic nitrogen. But they didn't see all four of these nitrogen peaks. Rather, they just noticed only two, which is the pyridinic nitrogen, about 398.2 eV, and about 401 eV. They saw graphitic nitrogen. And as you can see, majority of the nitrogen present in the structure is dominated by pyridinic nitrogen. And with this copper 2p, they can see the major peak about 933 eV is related to this zero valent copper ions. And also they have the presence of copper 2. This is around 934.6 eV, and the satellite peak is about 945 eV. So this confirms that the coordination with the nitrogen atoms to form the Cu2N. And so the pyridinic interaction, pyridinic nitrogen interaction with copper 2 forms this copper 2N. As the graphitic nitrogen affects the electronic and geometric carbon structure. Also, introducing copper metal into this nitrogen doped carbon structure can increase this proportion of OCO bond or an NO bond. So this actually promotes your initial onset potential. So that is a good characteristics of an overall catalyst. So moving on to this electrochemical evaluation. So they did all this electrochemical evaluation in alkaline medium. As you can see, they did the linear strip voltammetry, scanning from about 1.1 volt to about 0.2 volt with respect to RHE. But in their actual experiment, they used standard Kelamal electrode, and they did the conversion to convert it into RHE. And as we can see in the table summarizes the onset potential, the halfway potential, and the electron transfer number. I mentioned earlier in the presentation that you want, for an ideal overall catalyst, you want this electron transfer number to be close to 4. So they calculated this electron transfer number using the scale plot to identify what is the overall electron involved in this overall reaction. And so we can compare. So they started with ZIF-8, and then they, without any copper doping, they annealed it at 900 degrees Celsius, right? And then doped with copper ZIF-8, and they did it at 5 different temperatures. And they found that the temperature about 800 degrees Celsius gives the optimal parameter for achieving the optimum balance between this copper to nitrogen bond and also the copper 0 nanoparticles. And we can see that the resulting catalyst EUNC 800 has about higher current density, which is about 5.7, whereas their commercial catalyst that they tested has about only 5.1 milliampere per centimeter square. And they have a higher positive onset potential by about like 10 millivolts, and also 20 millivolts more positive onset potential. Also, their electron transfer number is close to 4, confirming that it is an efficient 4 electron transfer ORR process. And so this is to just show how the ORR curves at different RPM varies for this best functioning catalyst CUNC 800. As you can see, this is a mass transfer limited. So that's why you see this steady state plateau. But with respect to rotation rate, you will have more oxygen getting to your electrode. So you should have increase in the current density, and they could confirm that by changing the rotation rate, the current density indeed increases. And this, so the catalytic activity of this copper nitrogen doped carbon at 800 degrees Celsius, they attribute this to 3 factors. One is the porous structure present in the is very conductive to the electron transfer, and it also exposes active centers for ORR. And also they help in the transport of electrolyte and gas diffusion with the presence of mesopores. And the nitrogen doping in carbon matrix also promotes this catalyst activity. And the incorporation of this copper nanoparticles helps in improving the catalytic efficiency and also provides conductivity to this nitrogen doped carbon. And they tested the catalyst stability with a chronoamperometry. So initially, when they did the chronoamperometry, they did it for about 10 hours. And what they found was their CU best performing copper nitrogen doped carbon catalyst can had only a loss of about 1.5%, can maintain about 98.5% of the initial current. But whereas the platinum carbon lost about like 16.7% and maintained only about 83.3%, and the nitrogen doped carbon lost about like 24.4% and maintained only about 74.6%. So this tells overall, after cycling for about 10 hours, you can still have a very low loss and maintain a good stability for your copper nitrogen doped carbon at 800 degrees Celsius. And they also did this linear strip voltammetry. So basically doing a accelerated stress test for 1,000 cycles at a very high potential and at a very high scan rate between a potential of about 1.1 volts to about 0.6 volts with respect to RHE. And then they recorded the LSV. And maybe I think it's kind of like a mistake, I would say, or something is probably like when the plotting, there was some mistake. So their discussion section says that the initial activity and the LSB after 1,000 cycles kind of overlap, but rather what we see here is this after 1,000 cycles, indeed, they have a high increased activity. So, which I'm not sure how this could happen. But yeah, so overall, at least based on their chronoamperometry data, we can, they kind of identified that the higher pyridinic nitrogen content present in this copper nitrogen doped carbon is responsible for this higher stability. And the CuNC has an acceptable porous layer structure, and the copper manages its high large surface area. And so since because of this porous structure with micropores and mesopores, you have both exposed ORR sites and also you have a better mass transfer. And then the copper nitrogen doped carbon has adequate ORR active sites with a shorter channel length, and also it has a good mass transfer capacity with the high electrochemical activity. Also, then the presence of copper indeed increases the conductivity of the overall catalyst, which is very good for operating your ORR process. So as a summary, they prepared the CuNCX by using pyrolysis of ZIF-8 with doped copper nanoparticles using a new method. And the resulting catalyst had an outstanding ORR activity compared to the commercial platinum carbon catalyst. And it also had a good selectivity towards this 4-electron process. And the CuNC 800 had a higher stability compared to the platinum carbon catalyst and also to the nitrogen doped carbon without any copper. And this improvement, they say it's because of the high pyridinic nitrogen and also the ordered mesoporous and microporous structure, and also the improvement in the conductivity and in the rich nitrogen doping. So this way, basically the metal nitrogen co-doping strategy will significantly improve the catalyst catalytic performance. And also this actually this MNC provides this new guideline. Of course, a lot of researchers are working on this to prepare this non-noble nitrogen doped carbon-based ORR catalyst to kind of replace platinum carbon. So with that, I would like to thank you all, and then we can move on to the discussion.
Thank you, Ayyappan. That was a very nice summary. Comments, questions, thoughts from the team?
I was just wondering about the structure that it would take when they mix the copper nanoparticles with the MOF. So how do you think it would interact with, means already there would be zinc ions inside the cavity of the MOFs, and when we add the copper nanoparticles and also to form copper doping,
So
how do you think they would interact
I
with?
think it's the selection of ion is probably they chose copper because of the size between the copper and zinc. So I mean, based on my understanding, this is how it should work. So the zinc should get evaporate first, and then.
I'm just asking before annealing, when they mix, they should form some structure, right?
Yeah.
Only, when they are annealing, the structure of this MOF, it has to be retained, and it has to be around copper.
No, while annealing, you cannot maintain the structure. So there is a compromise. So while annealing, you actually break down the structure. So you lose the conductivity. And that's why people, when they try to make the nitrogen doped carbon from MOFs, they try to add additional support. For example, they add carbon support like graphene or something, or they also add like transition metals. Because you break down the MOFs, so you don't maintain the structure of MOFs anymore. You basically use the presence of a more high carbon content and nitrogen content and produce kind of like this amorphous carbon doped with nitrogen. So their conductivity falls back. So that's why they try to improve it by adding additional components like carbon, other conductive carbon structure or conductive metals.
And also, I think the authors, they did not confirm the interaction of copper with nitrogen. Have they done any like X-ray absorption studies, or like they have not found the coordination number of copper to confirm that it is a single atom, like it is interacting with nitrogen and then carbon. I guess that
Yeah,
was missing.
yeah.
Yeah.
When you say single atom, you should do the
Yeah.
near X-ray studies, but they
Mm,
haven't done any of those. But I think they
mm,
come to this conclusion that there were, when they did the XPS, right? So they had the
mm.
Cu2 plus, and they said the Cu2 plus could have been with nitrogen, and that they took it. So maybe calling it as a single atom catalyst, of course, you should have those Zans.
Yeah, at least they should
Confirmed.
tell the coordination number of
Correct.
copper.
Yeah.
Yeah, and also they could have done STEM mapping to show the single atom catalysts. I think that was also missing.
I
Like
think the paper was
dark
done.
field imaging.
They had just only one author, so
Mm, okay.
yeah, it's just one author doing everything, and yeah.
Yeah.
Also, one other thing, maybe kind of they maybe it's probably missed. I think while probably printing, or it was not included. Something they also talk about like the CV characterizations in their discussion section, but I couldn't find the CV on their electrochemical data, or neither on their SI. So I was just wondering, maybe some kind of mistake happened while printing or something like that.
Got it.
Like in XRD, were they able to see the presence of copper? Like I did not.
Yes, actually they did see that copper 111 and to the 200 on the copper ZIF-8.
Okay, okay. You were telling about the stability. Like there
Yeah,
was no difference in the structural.
yeah. But
That's what.
yeah, with copper they see, but once they anneal it with the copper on nitrogen doped carbon, they don't see the copper peak. That's because of their atomic percent is very low, right? It's about 0.46%. So the signal is very weak to be detected. So that's why when the XRD data, they couldn't see those two major peaks, which is very sharp on the copper ZIF. It cannot be noticed on the copper nitrogen doped carbon.
So, any other questions? A couple of comments from my side. One, I thought the paper had very good characterization for a single author paper. The author definitely went through all the characterizations and really established the structure before going into the electrochemical characterization. I thought that was a good thing about the paper. So one thing I felt creative was about the percentage current when they were comparing with platinum on carbon. So, and also I didn't realize they were talking about 74% and 85% degradation, but when I look at those plots, those are all very stable. So how did they calculate that percentage?
I think it's their initial current density and then the after. So initially you'll have a loss, right? At the initial, probably within an hour loss. So I think they did normalize it to their initial current density and then after 10 hours.
Yeah, but at least in the chart, maybe they cut off that initial section.
Initial section, okay, yeah.
I didn't see any drop, right?
Mm-hmm.
So
Yeah,
when
it felt more stable at the longer time, yeah.
Yeah, it was only total of 8 hours. That's different. I mean, that's one pet peeve for me when they talk about stability. 8 hours is not a long time from a stability of the catalyst point of view, but that's okay. I think given the academic constraints, that's probably okay. But I didn't see that drop in current. The other thing, again, I think if they had actually used the actual current, it would have been probably lower than the platinum on carbon. Maybe that's why they normalized it.
Yeah, but actually I mean, and this, I wasn't sure what potential they had this at normalized current was at.
True.
That could also be the reason. But when we look at the data, at every potential, the current of their copper catalyst is actually higher than platinum carbon. Even at halfway potential, it's always on the positive side of the curve.
Yeah.
But we can see on the XRD data, I can actually share the screen, the catalyst stability data.
Mm-hmm.
Actually, they see a change over here on the platinum side about in 30 minutes, I think. Within less than 30 minutes, they see this drop.
Right. When you look at NC 900 and
yeah, that I don't see anything. Yeah.
Right.
It starts about 75%.
Correct. So
Yeah.
that's what I didn't understand, how they calculated and how they attributed the stability of 75%.
Yes, yes, yeah.
Right. Yeah. Okay. And the other one I was thinking about, I think this is a more a practical side comment, is in addition to this efficiency being good with 4-electron transfer, it also impacts the membrane stability and other things. Depending on if you're using a polymeric membrane, you don't want peroxide impacting the stability of the membrane. Yeah, so that's a
So,
good thing to avoid the peroxide.
yeah, and also the transition metal, I think we have a ME on the acidic PEM more, right? So the
Correct.
naphthalene membrane. So don't know the compatibility of this catalyst on the like in the acidic conditions. All the studies were in
That's true.
alkaline conditions. So,
Correct. Correct. Yeah. Okay. If there are no further questions, next week we'll have Archana presenting, right? So
yeah,
what are we going to be talking about?
yeah, we'll share that screen.
Yeah.
Is on methanol oxidation.
Great.
Yeah. Why don't you go ahead, Archana? This is
Yeah, I've chosen a paper close to my own research. So it's evolution of composition and structure of PTRH in the acidic methanol oxidation process. So this paper, they were doing a very detailed study on the cyclic automogram, and they were explaining it very well on the methanol oxidation side. Like, generally, people they don't explain this much. I found it really interesting. So I think
Excellent.
it's good to
Great.
discuss that paper.
Looking forward to learning from you next week. And if you would like to lead this session, please send us an email at info@vetrilabs.com. Thank you for joining us. See you next week.